Okay, so here are the topics for the calculus-based physics test. So the first one is just vectors in general. So adding vectors, subtracting vectors. So what I'll do is I'll give you, like two vectors. Here's vector A, here's vector B, and I'll give you the magnitude and directions. So I'll give you, the magnitude of B is something, say 10, and the magnitude of A is 5, and these angles, and I could do them relative to the y-axis or relative to the x-axis. So that's 105 degrees, and this one is 30 degrees. And then, so what you would need to do is you would need to put it in component form. I mean, there's two ways you can do it. You could do vector A is equal to some magnitude times I plus some magnitude times j, and vector B is some I plus some j. Or you could do, A sub x equals something and A sub y equals something, and then B sub x equals something and B sub y. So you could break up into the components, and then you could show them as i's and j's. But then, to get your resultant vector, you're going to add, the components together here, or you're going to add it that way. So, and once you find the resultant, then I want you to find the magnitude of the resultant vector and the direction relative to the okay, so that's the first thing. The second thing is kind of similar to the first thing. So in this case, the first case, I want you to just use component form. The second problem involves using I and j notation. So if you have a vector A, it's going to be A sub x times I plus A sub y times j, and so forth. And so the resultant vector here is just the sum of the two, but if I told you vector C was 2 times vector A plus 7 times vector B or something like that. So here you've got a scalar multiple. So you break it up into the components. So you get what you do again is given some kind of magnitude and direction for vector A and some magnitude and direction for vector B. And then you break it up into the components, and then I want you to be able to represent them in an IJ notation and do the appropriate multiplication by a scalar and or addition or subtraction. Okay, the next thing I want you to be able to do is to take a position vector that's going to be r sub x. It's going to be a function of t times I, and then it's going to be r sub y times a function of t times j. So each one of these are functions of time. And so if I asked you to calculate the velocity vector, you would just take the derivative of the position vector with respect to time, which would have v sub x as a function of t times I plus v sub y times a function of t times j. So that's and then I might ask you to evaluate this velocity at a particular temperature, a particular time. Now, one thing I'm not sure if we've covered, but we've talked about in calculus, is if I wanted to calculate the average velocity for a particular time period, say from t equals 1 to t equals 3, what you would do is, if you remember, the average, I'm just going to do it from a calculus standpoint, the average value for a function is 1 over b minus a times the integral from a to b of f of x dx. So if I asked you to calculate the average velocity, and this is the average velocity is going to have both x and y components. This will be the average velocity vector. So average velocity vector. What you do is you take 1 over t2 minus t1, the two times you're finding the average velocity between integral from t1 to t2 of v of t, the velocity vector, times dt. So you'd integrate this and then evaluate that integral and then divide by the time over which it occurred. The reason I'm talking slowly is, the derivative of the position vector is the velocity vector. So I was trying to think if the average of the velocities is the same as the average velocity. Because if you integrate that, you're going to get that, because we took the derivative to go that direction. And then if you evaluate that, you're going to get the position at t2 minus the position at t1. So that's the change in position divided by the time. So I think actually I'm convincing myself that if I ask you for the instantaneous velocity, then you just plug it into this expression. If you want the average velocity, what you would do is you can just evaluate, the average velocity it's not the average of the velocities. Okay, so that would be the one thing you don't want to do. You don't want to evaluate the velocity at t equals 1 and the velocity at t equals 3 and say the average of those two divided by 2 is the average velocity. What you end up doing is you have the position at t equals t2 minus the position at t1 divided by t2 minus t1. And that's kind of the definition of average velocity from a vector standpoint. So you don't need to take the integral again. We just evaluate the position at these two times and then divide by that difference in time. Okay. Then when it comes to one-dimensional motion, I guess that kind of was a one-dimensional motion problem. Except that may actually this would be more than one dimension because you've got an I and a j component. But looking at those one-dimensional problems, what I give you there is, because it's one dimension, we'll call that x. X of t is just going to be some function of t, whatever that is. With it might be a times t squared plus b times t plus c. I'm just going to give you a polynomial, and so I want you to be able to derive the equation for the velocity, which is just the derivative of the position vector with respect to time, and then the acceleration value here is just the second derivative of the position vector with respect to time, or you can just take the first derivative of the velocity vector with respect to time. So you come up with the equations, and then you can again calculate the instantaneous velocity and the average values. So make sure instantaneous just means that you're going to plug in t into these equations to find v of t, particular time. And again, if you want to figure out the average velocity, you want to take the position. The average velocity is not the average of the velocities at the end and the beginning at the end. The average velocity between t equals from t1 to t2. All you have to do is take the x values of t2 minus the x value at t1 and divide by t2 minus t1. Okay, so that's another example. The third thing, this is the next thing. Remember, work is equal to the integral of the force vector dotted with the displacement vector. Now, what I'm going to do here is actually, that's not the one. Yeah, that's not what I'm asking you to do here. What I'm asking you to do here is if I if I give you a position vector again, r vector is a function of t, and it could be it could have three components. R sub x of t, r sub y of t, and r sub r sub z of t times k. Okay, so of course the position vector is the derivative of the velocity vector, the derivative of the position vector with respect to time, and the acceleration vector is the derivative of the velocity vector with respect to time. Now, if I ask you to calculate the force that's acting on this at a particular time, what you can do is you can take the acceleration vector, and we know from Newton's second law that the force vector, the net force vector, is equal to the mass, which is a scalar, times the acceleration vector. So if I know the acceleration vector and I know the mass, then I should be able to find the force vector. So this is just using Newton's second law, starting with the position vector, calculating velocity and acceleration vector, then using Newton's second law to calculate the force vector that has to be acting on that for that acceleration to be appropriate. Okay, so that's pretty much it. Yeah, I haven't put any integration. So there will be a calculus-based physics final, and I'll put some integration stuff on that. So don't think you're not going to do anything